Before I start, perhaps I should explain why I'm now first sitting here just after the very nice introduction by Sante. And the reason is that I actually once had the role of Sante. In between there was Pacom, and I was also RF of fundamental physics at ACT. And it was during my time when we started transformational optics at the ACT. I don't say it I started because it was not me alone. It was mainly together with my colleague Jose Lorenz Montorio, who's now in Madrid, and of course the whole group as usual in the ACT. So we started this project on transformational optics, and actually we had 4 parallel studies then. I think it never happened again.
Never ever.
And we explored, as now it has been explored on acoustics, we explored then on electromagnetics, how this works. And I have to say I really learned a lot from these studies. Now, then Sante asked me, can you present what you did during that study? And I said, well, it's a little bit difficult because these were technicalities that perhaps don't matter. Sorry, don't matter if you make a presentation about acoustics. But we agreed then that it would be a good idea to explain why is transformational optics so successful. And Sante already told it is the conclusion because it's pre-metric. So what is a little bit behind, one step back, not showing the nice figures of cloaks or beam shifters or whatever, but one step back, technical, what is the reason why we can play this game? My presentation should be short, introduction, the principle, and in the end, what it is and what it is not. The introduction, what do we want? What do we want to achieve? We are looking for a design strategy for artificial materials that should work for any polarization. It should work independently of the incident angle, and the functional principle and the material parameters, they are derived by a geometrical principle and in a completely algebraic way. And they are derived from simple, well-known situations. In most applications, the free space solution, but this need not be the free space solution. So we have our device. Here's our device. Inside this device, something shall happen. It shall happen. There shall not be any restriction on the polarization of the light, on the incidence angle, how this is done. And the way I designed this is just, well, geometry. It's very simple. The ray goes like this, and now I want it like this. I will show this in a few slides, and instead of formulas, I first just show pictures. Of course, these pictures are simplified. It's a little bit difficult to see the yellow, I realize. But let's say here we have our physical system. It's our laboratory or whatever. And in this laboratory, we have a dynamic. So here is our physical system. There is something happening. I indicate it just by an arrow. So something is moving from left to right. It could be the trajectory of light. It could be a point particle. It could be our acoustic wave, whatever. This is our physical system. Now, many people, notably engineers, like to use coordinates. So we can map this physical system onto coordinates. That's a very well-known procedure. So here, for example, for this 2D system, we have 2D Cartesian coordinates, the coordinate mesh, and the straight line in this thing. If you have these Cartesian coordinates and also represent the coordinates in the Cartesian way, then of course it's also a straight line, because it's essentially the same thing, just in coordinates. But nobody forces us to use these simple coordinates. Instead, we can use weird coordinates. Now these weird coordinates, here in between you see I did something weird. But I still decide that, of course, I just choose one axis, the x for one coordinates, the y for the other coordinate, and make this mesh. And then if I map this arrow onto this weird coordinates, it appears as if the particle or the wave would not longer move straight. But of course it appears as if, because this is just a weird coordinate, and the weird coordinate has absolutely no meaning at all. The only thing that has a meaning happens over here. Well, if the coordinates are well defined, all over the patch that I'm representing. There is, of course, the coordinate transformation from here to here and also back, because it works both ways. And what I did here, up here I have bar, down here I have no bars. I just made a shift that is x-dependent of the y coordinate. Okay, so that is the standard stuff that anybody knows. And now comes the point of transformation optics, or the transformation approach. Can I find a system, a different system, where this one here are the normal coordinates of this unknown new system, and this one here then would be weird coordinates? So that is the transformation idea. And the point is that, of course, here in the middle where something interesting happens, this system on the right cannot be equivalent to the system of the left, because there's something physically really happens. Now indeed the arrow is no longer straight, but it moves up. Here everything looks very, very simple, but you should realize that in physics we are not dealing just with arrows. In physics we are dealing with solutions of differential equations. And the claim that the solution of the differential equation of a simple system to the left, represented in weird coordinates, is equivalent to the solution of a differential equation of a somehow complicated system, this time again in Cartesian coordinates. This claim is far from obvious that this is possible. But in electromagnetics it's possible. And let me show why this is possible. I have to say here that I present a simplified version of the stuff, because those people who know the full version, they know it anyway. For those, I don't have to make the presentation. For the others, I avoid to have introducing a relativistically covariant formulation of electromagnetism. So therefore, I use the standard Maxwell equations. I have this, what one can call the Maxwell-Faraday equations. They relate the fields E and B, electric field and magnetic inductance. They say that time-varying magnetic field induces an electric field, and this famous equation here says that there are no magnetic monopoles. There is a second set of equations that looks almost the same. It has different fields, and most importantly on the right-hand side there is not a zero, but this time on the right-hand side we have a J and a rho, and this says that time varying of D of the electric displacement and a current induce the magnetic fields, and the charges are sources of the electric fields. And finally, we have a set of